Finally, we'll end this section with a very interesting example. So consider the map T from R to R, defined as follows. So T of x is 0 if x is 0, and if x is non-zero, it is 1/2 of x minus 1 over x. It will be helpful to draw a graph of this. So we have the coordinate system, and here's 1, and here's -1. You know this function is 0 and -1 and 1. And by taking the derivative of this when x is not equal to 0, you get 1/2 plus 1/2 times 1 over x squared. So the slope will approach 1/2 as x goes to infinity, as well as negative infinity. So there will be an asymptotic line with slope 1/2. And the function will look like this. So it has value at 0, and on the positive axis, on the positive real line, it is a monotone increasing function from negative infinity to positive infinity, and symmetrically on the negative real line. It goes from negative infinity to positive infinity. And this curve is a hyperbola. Now, for any L1 function f, namely for any integrable function on the real line with respect to the Lebesgue measure, you consider substitution y equal to t of x. And you can prove the following equality, that the integration from negative infinity to positive infinity of the function f of tx integrated against is same as the integration of f of y integrated against this measure. So let's first check this equality by the change of variable formula in calculus. So let's check. So remember, t of x is equal to 0 if x is 0, and 1/2 times x minus 1 over x if x is non-zero. And let's call this y. The first thing we want to do is that for the case when x is not non-zero, you want to solve this equation for x. You want to express x in terms of y, so that you can do the change of variable formula in here. So by some calculation, you will get x equals y plus minus y squared plus 1. This is for the case when x is non-zero. And if x is greater than 0, you get x equals y plus y square root of y squared plus 1. And if x, if x is negative, then x equals y minus y squared plus 1. So this is essentially done by solving this quadratic equation. Because when you multiply both sides by x, you get a quadratic equation. And you just solve it with the formula you know. Now we start with the left hand side. The left hand side is equal to, first of all, there is something we have to be very careful about. You should note that this map is not bijective. It is actually 2 to 1. You can see from the graph here that if you take any level set, it hits this graph at 2 points. So this map is really a 2 to 1 map, not injective. So you cannot simply plug in t of x equals 1/2 of this directly into this and use the change of formula you know, change of variable formula you learned from calculus. You can't do that. In order to use the change of variable formula, you have to choose a domain where this t of x is really injective. So the trick is that you want to split the left hand side into 2 parts. The first part is from 0 to infinity, and the second part is from negative infinity to 0 of the same integrand. Now, when you restrict this function to the positive real line and negative real line, you can easily see that in that case, t of x strictly monotone and thus injective on those 2 pieces separately. So now you can use the change of variable formula directly. What you do is that, so in here, this t of x is just y, and you also want to plug in x equal to y plus minus the square root to those 2 places separately. And the first part, let's first look at the first part, is equal to, now when x ranges from 0 to infinity, y actually ranges from negative infinity to infinity, as is given in this graph. When x is from 0 to infinity, y is from negative infinity to positive infinity. So the first part is really equal to the integration from negative infinity to positive infinity of f of y times, now you want to take the differentiation of both sides of this. What you do is that you take d of now x equal to y plus square root of y squared plus 1, and now you divide this guy by 1 plus, what is x squared? X squared is y plus 1 plus y squared square root, and you raise this guy to the squared power, and let's first forget about the second term. So you simplify this integration, what you get is that, so in the numerator you get dy is coefficient 1 plus, the derivative of this is y divided by square root of 1 plus y squared. And in the denominator you will get pi times, this will be 2 times y squared plus 2 plus 2y square root of 1 plus y squared. And now you simplify the numerator and denominator. And what you get in the end will be dy divided by 2 pi times 1 plus y squared. So this is the first part. Then how about the second part? Of course, you can do this computation again, but another lazy way would be to observe that that this t of x is an odd function. So now you first do a change of variable by changing x to negative x. Then this t of negative x will range from positive infinity to 0. And there's a flip sign here, so the integration will be like the integration from 0 to infinity. After you pull out the negative sign here. So anyway, in the end, you will see that the second part will be same as the first part. And of course, you can do this computation again. The computation effort will be the same. So you get the same thing. And this equals the integration from negative to infinity f of y times dy divided by pi times 1 plus y squared. That's it. So we just verified this equality. And if you teach calculus, be that recitation or lecture, you might want to test your students with this very interesting calculation, the change of variable formula. Because I guess most students may not be able to notice the subtlety in here, that this t of x is actually not bijective, and you cannot plug in this formula directly into this integral. So you will be able to educate your students a lot through this simple example. And by the way, although this is very obvious to you guys, I should emphasize that the value when x equals 0, which is 0 for t of x, is not important at all for this verification. Because at that point, you just get a f of 0. You can ignore the integration at just that one single point, because that single point has the back measure 0, which doesn't contribute to the integration of this, because we also assume that f to be integrable.